Hello everyone. Today we are going to study about Karnaugh maps under the subject that is digital circuits and systems. Our learning objectives will be, after this class, you will be able to create and label 2 variable and 3 variable K-maps. You will also be able to use K-mapping technique to simplify logic designs with 2 and 3 variables. Students should also be able to use K-mapping technique to simplify logic design containing don't care terms. Now, actually what is K-map? K-map also, which is a short form of Karnaugh mapping, is a technique. It is actually a graphical technique to solve questions related to algebraic expressions of Boolean algebra. In this we see, suppose if we find out a question over here, the function is provided that is f is equal to a bar b c or a bar b c or a bar b bar c or a b bar c. Now if we have to solve this equation, what we do, if we try to solve it with the help of Boolean algebra, we do use different theorems, that is De Morgan's theorems and other formulas, to solve it down and find out that f is equal to a bar b plus b bar c. This is the final equation which we find out if we use Boolean algebra simplification method. But if we are using a K-map simplification, it makes it quite more easier for the user to find out the simplified form of this equation. This equation which we are using. Let's see how. In this, we use these literals, that is the variables over here. We have 3 variables, that is a, b and c. Let's say a, b are here and c bar and c are put over here in a K-map with cells where there are 4 rows and 2 columns. Now in these 4 rows, the 2 different cells cannot vary more than 1 literal. That is, see here, if we are taking 2 variables a bar and b bar. When we go to the next state, we are seeing a bar is same, whereas we are changing b and b bar. That is, there is a 1-bit change. Similarly, when we go down to the next level, it's b has been kept common, and now this time a bar changes to a. In the next state, a is kept common and b is changed to b bar. So in this way we can see there is a 1-bit change, and over here we are taking c bar, adds 1-bit changes c. Now the terms which are available, that is a bar b c bar. Now a bar b c bar, this and this term combine to form this literal. So we put over 1 over here. Here is the 1. Now next term is a bar b c. Now a bar b over here, a bar b is this and c is this, a bar b c. So this term is 1. Similarly, we put all the variables and we find 1, 1, 1, and there is one don't care term. Why we are taking this don't care term to solve out? Now if we see this, we are making a pair of 1 over this side and the other one this side. This 2 makes a pair of 1 each. Now we can make a pair of this as well, but if we make the pair of this, now if we are making the pair of this 2 ones, the first one, what we get is a bar b bar c plus, that is or a b bar a b bar c. Now in these two, what we find is that B bar C is common. B bar C is common, and it comes out to be A bar plus A, which gives us B bar C. So this pair provides us B bar C, whereas this pair 1 and the don't care term provides us A bar B plus C bar plus A bar B C, and if we take out A bar B as common, C plus C bar makes it A bar plus B. So this shows how we can solve it more simplified, in a simplified way, in comparison to the Boolean algebra simplification, whereas both the outputs are same. We are getting the same output on both the sides. Now, what is actually a K-map technique? What we were seeing in the last slide, it is a graphical technique which is used to simplify a logic equation. It is a graphical technique used to simplify a logic equation. K-map are procedural and much cleaner than Boolean simplification. As we saw, we don't need to learn too much of the formulas. We just need to remember a few of the important formulas which is already known to all of us. Now K-map can be used for number of input variables, but practically it is easier to use for 2, 3 and 4 variables. Above that, the K-map becomes very complex. Now, what is actually the K-maps format which we saw in the last slide, which we were using earlier? Now we will see how its format is. Let's see. In this, each term in a truth table corresponds to a cell in the K-map. So, as we know that truth table, in that case, each min term is corresponding to a cell of K-map. That is, this cell, suppose this is a cell. This cell corresponds to a truth table where there are 3 terms, A bar, B bar, C. That terms is not actually present in the equation, so it's 0. K-map cells are labeled such that both horizontal and vertical movement differ only by one variable. This is very important to note. It differs by just one variable. This is what we saw in the last slide. In this case, C, this A bar is kept common, this B bar becomes B, here A bar becomes A, here B becomes B bar. So this is what it's saying, it's differ by just one variable. Since the adjacent cells differ by only one variable, they can be grouped to create simpler terms in SOP expression. So as they are differing by just one variable, they can be grouped in easier terms for forming SOP expression. The SOP expression for the logic function can be obtained by ORing together the cells or group of cells that contains 1. This is how we found that this pair we saw over here, this pair, this and this and this, these two pairs formed, one provide us B bar C, one provide us A bar B, and they are formed with the help of OR. Now, simplification. This is very simple to simplify a term using K-map. Here we are seeing this one present, this one present. This one corresponds to W bar X bar, this W bar and this X bar. Now this one corresponds to this W X bar, so it becomes W X bar. So this cell can be written as W X bar, whose value is 1 because it's present. So because it's present in the equation, whichever equation we are considering. Similarly, we can find out, and now this term is W bar X bar, that is W bar X bar, that is also equal to 1. And now if we can see that these two are forming a pair of 1 over here, so this can be taken as the addition, the ORing of the two adjacent cells, that is Wx bar plus W bar X bar, which provides us as X bar as common, W per W bar, W plus W bar, and that gives us X bar. Final output. This is here X bar, which we found through logical simplification. So this is how we simplify the two adjacent cells. Now, let's say there is a truth table of a two variable K-map. In this case, this is the truth table with two functions W and X, the value 0, 0, 0, 1, 1, 0, 1, 1. We found out, let's say this is the output. When you provide these two minterms, when we provide this value to the function to which this truth table corresponds to, its output is 1. For 0, 1 it's 0, for 1, 0 it's 1, for 1, 1 it's 0. So these are minterm 0, minterm 1, minterm 2, minterm 3. Now these minterms are put in the K-map in this way. This 1 is put over here, this 0, this 1, and this 0. This forms the K-map. Now the K-map for one group, there is 1, so it's A bar B bar corresponding. This is A B bar, this is A bar B, and this is AB. Now groups of 2, 4. Now this is 1, 1, this is a pair, this is the second pair, this is the third pair, this is the fourth pair. Now this is a quadrilateral. This is a quad formed in a K-map, and for this the output becomes A plus AB. Now the simplified form of steps for simplification process of K-map. First, we construct a label for K-map. We place ones in the cells corresponding to ones in the truth table, place zeros in the other cells. Now we identify and group all isolated ones. The isolated ones are the ones that cannot be grouped with any other one, or can only be grouped with one other adjacent one. Then we look out for any hex, that is, if there is any formation of 6 ones. Then we look for octet, that is 8 ones, even if it contains some ones already grouped but enclosed in a hex. Group any quad, even if it contains some ones already grouped but enclosed in a hex or octet. Group any pair, and then OR together all terms to generate the SOP equation. Now the example for a two variable K-map. It's a JK flip-flop. Let's say for 0, 0 it's 1, for 0, 1 it's 1, for 1, 0 it's 0, and for 1, 1 it's 0. So we form the two ones are put over here and here, minterm 0 and minterm 1, and rest two zeros are put over here. This one is here and this one is here. So this forms F1 gives us J bar. Now for the three variable K-map, similarly we form the K-map truth table, and here is the K-map for that. One that can change, and it provides us the final. These are the two ones, pairs of ones which can be formed. Then a group of hex, Now group of 8.